If we want to approximate this area with one trapezium, the approximation is not that great because of this error here. But simply choosing to go with two trapeziums instead is much better because our error is a lot smaller now. So it's a lot more accurate with two trapezia rather than one. Now, in order to calculate the total area of the two trapezia, we'd first focus on this trapezia here. And so we need to come up with some notation for this x value. Now, it's common to start with x0 and end with xn. That way we can have as many different trapezia or subintervals as we like. In this case, that means that this value would be what we call x1. Okay, but if we had more, we could start with x0 and then go x1, x2, x3, x4, x5 until we get to our final x value. So now that we've given a name for this x value, we can use the trapezium formula to work out its area. Half times the height. Now keep in mind height is now this distance, and that's going to be the same as the height for the second trapezium as well, because we always equally space our trapezium. So that's our height, that distance in there, and then we have f of a, so that's this first parallel side, and then f of x1, which is this second parallel side. But this is just the first of our two trapezia, so what about our second one? Well, this is just going to be very similar, except we'll be using x1 and b. So we have this same side being used again, so f of x1 plus f of b, and then we've got the half h out the front. So to get the total area, we just need to add these two areas together. So the total area will be area 1 plus area 2. Half h is common to both, so we can drag half times h out the front. And then what do we have left? We have f of a plus f of x1. So f of a plus f of x1, but then plus f of x1 again. So we're going to have two lots of f of x1, and that makes sense, right? This middle line belongs to both the first and the second trapezium. So we're going to have one lot of fa and one lot of fb, and two lots of f of x1 when we add this red line with this green line. But just like before, is there a way to actually get rid of this h and write it in terms of something else? Well, for this specific example, notice that xn is actually x2 because we have two trapeziums or two subintervals. And because we break the total distance between a and b into in this case, two even segments, that means that our h value is the total distance, b minus a, divided by however many, in this case 2, subintervals or trapezium you have. So for this specific case, we could say that it's 1/2 times b minus a on 2. That's our h value. Although in general that could be n if we had n trapeziums, and then we still have the same thing as above. So let's write this out properly for that more general case where we have n subintervals. So we start at a, or we might call this x0, and then our next x value is x1, then x2, then x3, and so on. We keep going, counting along until we get towards the end where we have b, okay, or maybe that's xn, our nth value, okay, and so the one before it would be 1 less than n, xn minus 1. And so each height of each of these lines is just going to be what we get when we sub that particular x value into the function. So f of a, f of x1, and so on, all the way up to f of x. Now this is n minus 1, and this is the last one, f of b. Okay. What about the height? That is just the equal spacing that we get for each of these trapezia. So all of these are a value of h, this distance, and this last one here. So how do we calculate that value of h? Well, it is just the total distance, b minus a, divided into however many of these trapezium you have. And in this particular case, because we're looking at the generalized example, there are n of them. So b minus a over n. And finally, before we write down this formula, remember in the previous example how we got x1, this length here, this f of x1, it was used twice, right? Because it was part of the first trapezium and the second trapezium. Well, now the same thing is going to happen, but also with f of x2. It'll get used for the second trapezium and the third trapezium, and so on, all the way up until this value, f of xn minus 1, the second last one. It'll get used twice. So every single parallel line is going to get used twice, except for f of a and f of b. So that means our formula can be written like this. The area is approximately equal to half times the height times the very first parallel side, f of a, and the last parallel side, f of b, and then 2 lots of everything else. Right, so 2 lots of everything else. Use some different brackets here. So we have f of x1 plus f of x2 plus f of x3 all the way until that second last value, f of xn minus 1. Getting cramped. Or if we wanted to use the fact that h is just b minus a on n, have a think, what will happen when this fraction is multiplied by a half? Well, the 2 will just come down the bottom to join with the n, and so we get b minus a on 2n out the front of that big sum there. Okay, so I know it can be a little bit confusing when we talk about a general example like this, okay, where we're not dealing with a specific number, but rather just some n number of trapeziums or subintervals. But let's do an example now and put this into practice. Use the trapezoidal rule with 4 subintervals, so we can see there's the difference to the example we did last time. Not just the trapezoidal rule, but the trapezoidal rule with 4 subintervals to find an approximation for the integral between 2 and 3. Okay, so this is the area under this function between x equals 2 and x equals 3. Now, it's the integral of 2 over x minus 1. So this is another hyperbola. If we compare it to our standard hyperbola, 1 on x, it's been shifted across to the right 1. Right, so you notice that x cannot equal 1 on the denominator, so we're going to have a vertical asymptote at x equals 1, and then this 2 just stretches it vertically by 2. Okay, so let's draw this and see what we're dealing with. So we have a vertical asymptote at x equals 1. Okay, so draw that as a a dotted line. Now at x equals 2, when we substitute that in, we get 2 over 2 minus 1, so that's 2 over 1, or 2, so around here. And at x equals 3, we get 2 over 2, which is 1. So we're going through this point here. So we've got our hyperbola function coming down like this, and we are after this area between 2 and 3. However, we're not going to approximate it with just one trapezium this time. We're going to be using 4 subintervals, or 4 trapezium. And we want to make sure that they're all evenly spaced. So they're each going to have a width of 1/4, right? Because this overall width is 1, and then we divide that into 4. So 1/4 each. Before performing the calculations, it can be really useful to draw up a table for each of the x values along here and their corresponding f of x values. So like this. Our first x value is 2, and our final x value is 3. And what about the ones in between? Well, this very middle one will be 2.5, and then we can see in between that we have 2.25, and over here we have 2.75, right? Which makes sense, they're all spaced by 1/4, like we were saying. Now this is a good place to note that 4 subintervals means that we'll have 5 values, right? So you always have one more value than subintervals. Okay, now what about the fx values? This is where we substitute in the x values into our equation, and we can write that here as well. So this is just splitting it up so that we're not doing it all in the formula all at one go. So 2 and 3, we already worked those out. When you sub in 2, you get 2. And when you sub in 3, you get 1. But what about these guys? Well, that's where we'd go to the calculator. 2 divided by 2.25 minus 1. This gives us 1.6. Okay, that's nice. 1.6. When we substitute in 2.5, so let's try it with when it's just 2.5, we get 1.3333 repeater. Now I'd recommend that you store this value or use 1 1/3 so that you've got an exact value. And 2.75. What happens at 2.75? We get another decimal. So I'll write it as 1.14, but once again I would recommend that you store that value. If you don't know how to store, once you have your answer written here like this, STO stands for store, so it's in gold, so we'd press shift and then store, and you can see STO is up here, and then you can choose the letter that you want to store it as. So if I want to store it as A, it's now telling me that my answer has been stored as A. But A is in red, right? So when I want to go and access this, I've got to use alpha to access that. So here's our formula. B minus A over 2n, and that's multiplied by f of A plus f of B plus 2 lots of everything else. So I'll give ourselves a little bit more room here. Okay, let's start plugging in some values. We know that B is 3 and A is 2. And that's over 2 lots of n is 4. We have 4 subintervals. And then in the brackets, we have f of A, so that's our first function value, 2, plus f of B, that's our last function value, 1, and then that's times 2 lots of everything else. So 1.6 plus the 1.33333, or the 1 1/3, plus 1.14. Now remember, I stored that value in the calculator, so it's got a bit more to it. But I'll just write 1.14 for now. If you like, we can tidy up the first part. So let's think about this. 3 minus 2 is 1, and 2 times 4 is 8. So this is going to be 1/8. And then we have 3, 2 plus 1, plus 2 lots of whatever this number is. So let's calculate that now. I'll just show you, let's say I've cleared, okay, the value is still going to be stored as A. So I've got 1.6 plus 1 1/3. Now I want to use a mixed fraction, so shift and then the fraction button. And this is where, instead of writing 1.14, I'm going to go and retrieve it. So alpha, so the little a there, and then click A. So that is my exact value. And there you go, 4.076, etc. So we'll write that down here, 4.07, etc. And we can do our final calculation by plugging it all into the calculator. And to 3 decimal places, we get 1.394. And with that, we're finished. Good job.